Related rates are very important problems, and apparently in the book they say that it's the heart of Newtonian mechanics, and they say that calculus was invented to solve related rates problems. Okay, so and most related rate problems talk about things moving at different rates. So if like this planet is moving at this rate and this planet over here is moving at this rate, then you can figure out like what rate your planet is moving at. Or if a gear is turning at one rate, another gear is turning at another rate, what rate is something happening, or if something's going away, something's falling, something's moving, you'll see. But it's taking, related rates, you're taking derivatives with respect to time, okay? And whenever, so you can take, we've been taking derivatives with respect to x or with respect to y. We've been doing some with respect to time. But with related rates, since a rate is how something changes over time, related rates always involve like dx, dt, dr, dt, dy, dt, and that kind of stuff. All right. So, so a algebraic related rates problem might look something like, so D, this is the example that I stole from the book, okay? D, I stole all the examples from the book because it's hard. It's not that hard to make up your own related rates problems, but after doing all your homework problems, I didn't feel like making up a bunch of related. So related rates, so say this equation, what this represents, they say, is if you have one differentiable function which determines x, like a parametric equation, one function determines x and another function determines y, and it's a particle moving along a curve. So maybe x is doing one thing and y is doing some, so that you'd have like x of t and y of t. And if x is doing one thing over time, so this is time, and y is doing something else, okay, then you come up with some kind of equation and or some kind of curve, right? And if you want to know the distance of a point from the origin, okay, like the distance from here to here, or the distance as that point moves from here to here, it can be found by going, so this is a point x, y, and this describes its move. So this is an x, this is an y. Well, there's three parameters. There's x is doing something, y is doing something, and it moves over time. But if I want to find the distance, I can relate that by that. But if I want to find how the distance is changing, if they say find dd, dd, dt, okay, that's equal to the derivative of this with respect to time. And the way I take the derivative of that with respect to time, this is like this thing raised to the 1/2 power. So that would be just like you're doing the derivative normally. It'd be x squared plus y squared time to the negative 1/2, right? Times the derivative of the inside function. Well, what's the derivative of the inside function? 2x. However, anytime you take a derivative of something, you have to multiply it because you want the derivative with respect to time. So you have to multiply that by dx dt. Okay? dt. So times this plus the derivative of this with respect to time, which is the outside function, which is y squared, times the derivative of y with respect to t. So when you're doing a related rates problem, you're looking for how something changes. So if you want how that distance changes over time, you would have to know some point. So a problem would look like when x equals 5 and y equals 3, x is moving so fast, y is moving so fast. How fast is the distance changing from the distance from the origin changing? And you will, in all of these related rates problems, you can only have one unknown, right? So they'll give you like x, and they'll give you like y, and they'll give you like dx, and they'll give you like, dx dt, and they'll give you dy dt, and you have to find dv dt. Or vice versa. They'll give you 5 of the, so there's 6 variables there, right? There's how fast x is changing, how fast y is changing, and this usually represents at what point in time, because it's going to be changing at different rates depending on where you pick it, right? So if you like throw a ball up into the air, right, the rate of change changes, right, depending on where you are. Yes? No? Okay. So let's do kind of a better related rates problem. Oh, I should have done this on my nice teaching notes that I made up. 5 watch this. Watch, I copied everything. I'm a cheater. Open. What? Uh-oh. Did I just stop the video? No. Yo. What did you say? Why is it not there? Hold on. We have to pause the video. Straight. Okay. Yeah. So, yo, we're recording now. Where'd my thing go? There we go. Okay. Assume that the radius of sphere is a differentiable function. So this is where you do have to know some formulas. And I'm going to do the related rates problems, and I'll talk about these rules that they give you for solving related problems. Assume that the radius of sphere is a differentiable function of t, and let v be the volume of the sphere. Find an equation that relates dv dt and dr dt. Assume that the radius are in height of h. Oh, and that's the second part. So for the first part, let's see if I can move these out of the way for now. So the first part, first you just set up the volume of a sphere. Who knows the formula for volume of a sphere?
4/3 pi r cubed.
Very good. Okay, 4/3 pi r cubed. If you didn't know that, I don't know. I think they would probably give that to you on a test. If you really didn't know, I'd tell you. But you should kind of get familiar with some of these formulas. Okay? So all you have to do, dv dt, is just dv dt equals 3, right, times, I'm going to take the derivative of this with respect to r, and then multiply by dr dt. Okay? And so it's 3 times 4/3 pi, because the radius is changing, right? Doesn't it say that? Assume that the radius is differentiable function times dr dt. Okay, so whenever you take, it's just you take the derivative of something, and then you have to apply the chain rule by multiplying by dr dt, or whatever the variable is. And that it simplifies to dv dt equals, this goes away, 4 pi r squared dr dt. So they might ask you a question, which they will later on, like how fast. They don't have any specific numbers here right now, but they might say if the radius of the sphere is changing by 5 inches per second, right? At the point when the radius is 10, that's kind of extreme. Maybe it's changing by 1 inch per second. At the point where the radius is 10, how fast is the volume change? Okay, so that would be a related rate problem. We'll do some, you'll see them. Okay? This one is kind of similar, except you have 2 things going on. Okay? So if you want to do this one, assume that the radius and height of a cone are differentiable functions. And you got to be really careful. You got to make sure which things are changing and which things are not changing when you're looking at these functions. Okay? So it does, if they say they're differentiable functions of time, that means that they are changing. Okay? And we talked about the volume formula for cones, which is 1/3 pi r squared h. If it says something's not changing, then you just leave it alone, you pretend it's a constant. But it says both of these are differentiable functions. Find an equation that relates dv dt, dr dt, and dh dt. So in this case, you just dv dt, okay, is equal to, what I would do is pull out the constant in front. Okay, so instead of calling that 1/3 pi, I'll call it, there's a pi over 3 in front, times the derivative of r squared times h, right? Which is 2r 2r times h, I'm going to put dr dt over here, because I just took the derivative with respect to r, right? And now I'm going to take, now I'm applying the the product rule. So now I'm going to take the derivative of r squared h, where h is the thing that I'm going to take the derivative of. So that's called dh dt, right? Because the derivative of h is 1 times dh dt. So that's going to be r squared times dh dt. And that would be the derivative, how the volume is changing with respect to the time, right? So you could say if the radius is changing by this much per second and the height is changing by this much per second, and r is this and h is that, how fast is the volume change? Okay, so that's how you set those up. That's what's wrong? It's a little crazy, yeah, but they're fun problems to solve. Okay? So
the first one also work for DRDT. It says relates for DRDT.
does the first one, what do you mean? Where? What's,
Are we going to find DRDT too, or is it the same thing?
we did find DRDT in terms of dVdt.
Oh, okay.
Yeah. Okay? So here's some rules that they say work for solving problems. Look at how I can do this. Move these around, make them bigger, smaller.
That's awesome, Mr.
Isn't that amazing? I'm on the cutting edge. How come those things are underneath though?
Bring to the front, bring to the front.
Can you do that? I don't know. Let's just move. Okay?
Just put them on a new page, Mr. Leader.
I don't know how to do that. Where was that? What did I just move there? Okay, let's. Is there an option that says bring to front? Preferences. I don't know. I don't want to mess things up. So let's go back. Maybe I could just copy this. Edit. File. Where's the edit? Isn't there a copy?
Yeah,
Oh.
file. Edit. Yeah, that's good.
That's the second
job.
part. Wait, I'm not done yet.
Oh, you're not done?
No, because
Oh.
I have to copy this first. File, edit, copy, and I'm going to go back to this page. I'm going to go file, edit, paste. There. So now, this gives you a bunch of steps. What is this? I don't know. Oh, I accidentally copied too much. It's okay. So here's a bunch of steps for solving related rate problem. Understand the problem. So it's really important that you know these steps. You don't write all this down, but just thinking about it. Understand the problem. In particular, identify the variable whose rate of change you seek, and the variables whose rate of change you know. So maybe you're looking for the change in volume with respect to time. Sometimes you'll be looking for the rate of change of the height with respect to time, and so on. Develop a mathematical model, which is what we just did. Draw a picture. Many of these problems will involve geometric figures. So it's really important to draw a picture. Be sure to distinguish between what is being held constant and what things are changing. Okay? So sometimes you'll have a cone where both the radius and the height are changing. Sometimes just the radius is changing. Write an equation related to variable whose change you seek and whose rate you know. The formula is often geometric. Okay. Differentiate both sides implicitly with respect to time. The chain rule will be critically important to you. Okay, so we kind of talked about that. At the end, after you've done the differentiation, then you substitute in the things you know. So it's really important that you don't plug in what they give you before you do the differentiation. Okay, and freezes it, makes the picture changeable, and be able to interpret the solution. So let's do one where you actually have to find something. All right. So I'm going to drag this down here. So you have a rising balloon. And I stole these from the book. It's okay. I can steal things from the book, right? So a hot air balloon is rising straight up from a level field is tracked by a rangefinder 500 feet from the liftoff point. At the moment, the rangefinder's elevation is pi/4. The angle is increasing at a rate of 0.14 radian. How fast is the balloon rising at the moment? So what do you want to know? You want to know, how would you represent that in terms of a rate? Very good. You want dH dt, and we'll draw a picture in a minute, okay? You want dH dt, you know, what do you know?
It's 114 radians.
Right, what is 0.4 radians per minute? How fast the angle is changing. Usually in calculus, since we're smart, we call that d theta dt. Okay? Understand that? You know d theta dt. You also know, or you're given, you want this. So, and these are the things, so now you're going to find these things at a specific point, because these rates change depending on these other things. So you know that it's 500 feet, 500 feet from the liftoff point, and at the moment it is pi/4, and you know you want it when this thing is happening at pi/4 is the angle. Okay?
Can you draw a picture?
Yes, I can. You want me to draw a picture of this?
So with like cool half circles and stuff.
There, I drew a picture.
Oh.
Okay.
Nice.
Yeah. Pretty cool. I had that hidden, but I just made it. I had it minimized. So I was going to draw the picture, but I.
Wait, so it's rising straight up?
Yeah. So yeah, it's you really have to draw a picture. So what's happening here is 500 feet. So you're standing 500 feet away from the balloon, right?
Oh,
And the balloon is going up,
I got it.
and it tells you how fast this angle is changing in radians per minute. And this is a constant 500 feet,
So
right?
is that a constant velocity? Is that a constant change of 0.14?
Yeah, the radius, it's continually changing, so it's rotating. So this angle is increasing. At the moment, the rangefinder's elevation, the angle is increasing at the rate of 0.14 radians per minute. Maybe it's, I think that probably that angle is a constant, right? Because it's just going around, I'm not sure it is, but they tell you. Yeah.
Goes underneath the camera.
Yeah. I'm not sure, but they do tell you the rate at that point. So you can figure out the rate at that point. So they want to know how fast is the balloon rising, basically, right?
Oh, yeah, that's easy.
So all you have to do is write an equation that relates all these things. So what's the equation that relates this? Tangent of theta equals h over 500, okay? And this doesn't have to be a variable because this distance doesn't change, right? That thing's the same. All right. So now you're going to take d theta. You know d theta dt. So you're going to take the derivative of this implicitly. So you're going to go d theta. Whoops. Sorry. First you have to take the derivative of tangent theta. What's the derivative of tangent theta? Positive secant squared. Secant squared theta times the derivative with respect to theta, which is d theta dt, and equals 1 over 500, because that's a constant, times the derivative of h with respect to t. What's that? Just plain old dh dt. See? You get that? Okay. So I take the derivative of both sides, and I take the derivative of the outside function, which is tan of theta, but then I have to take the derivative, I want the derivative with respect to time, so I have to multiply by d theta dt. And then I just plug in stuff that I know, okay? I know that this is 0.14, right? I know that this is 1 over the cosine of theta, which is pi/4 squared. Maybe I should move down, right? So this is, so what you get is 1 over cosine of pi squared, right? Because it's secant squared is 1 over cosine, and I don't know how to do plug in numbers for secant, but I know how to plug in numbers for cosine.
Isn't it pi over 4 squared?
Oh, pi over 4, sorry. Pi over 4, sorry. I didn't read the problem. Let's erase my boo-boos. Good? What is this thing? Oh, that's a time sign. Times d theta dt, which is 0.14, equals 1 over 500 times dh dt, which is what I'm trying to find. So they say in the book, solve this for dh dt and then plug in the numbers. Doesn't really matter, okay? Cosine of pi over 4, anyone remember what that is? Root of 2 over 2. So it's 1 over root of 2 over 2 squared times 0.14, okay? And 1 over root of 2 over 2 squared is 2 over 4, which is 1/2. So this quantity right here comes out to be 2. Did you know that? 2 times 0.14 equals 1 over 500 dH dt. And so that you get that dH dt, what is this letter? dH dt is equal to 0.28 times 500, or 1,000 times 0.14, which comes out to be 140 feet per second. So you should put your unit, and that's how fast the balloon is going up. All right? So they get tricky though.
That was tricky.
That was tricky. We have to pause. And start my video. Sorry. Anyway, here's the problem we're doing. Sorry we got ahead of you. Okay. So plus 2y times dy dt equals 2z times dz dt. dz dt. All right? And so that's a z. That's a squiggly line. dz. 2, that was a 2. 2z times dz dt. All right, so then you plug in stuff. X, you know, is 0.8. So, oh, the other thing I can do is cancel out a 2 from all these, right? Which makes my life a little bit easier. And so now I know X, whoops, now I have to go up to look at my problem. So I know that X is 0.8, right? And what I'm trying to find is dx dt, so I don't know that yet. But y is 0.6. 0.6. And dy dt is what? This is where you have to be careful.
60.
It's actually negative 60 because he's moving closer. He's moving down. That distance is decreasing. You understand that? Because the distance from this point is decreasing. So that's a negative 60. So you have to be careful with that. That if things are increasing, then they're positive. If things are decreasing, then they're negative. Because he's coming toward this way, right? So that would be considered a negative velocity. Okay, equals z. Z is just, yeah, let's do a little problem. So z is going to equal to the square root of 0.6 squared plus 0.8 squared. And very conveniently, that comes out to be what? 1. Isn't that nice? Okay, so z is 1. And dz dt, it does say that the distance is increasing between them by 20 miles an hour. Okay? And then you just solve that for dx dt. So you get that 0.8 dx dt. What?
Oh, okay.
You want to solve it? So,
No, never mind.
so this is 20.6 times 60 is 36. So that should be, it's minus, this becomes minus 36. So you're going to add 36, right? And so dx dt, right? Dx dt just becomes 56 divided by 0.8, which is 70.
Why is
So-
the 20 not negative?
Because it says the distance at the beginning of the problem, it says that when the cruiser is 0.6 and the north and the inside the car, the police determine that the distance between them is increasing at 20 miles an hour. Okay? So that distance is increasing. If it was decreasing, then it'd be negative. All right? So that's, and determine it, you have to say what does that mean? He's the criminal, the bad guy is going at 70 miles an hour. Okay? The car is going 70 miles an hour. The deer
That's that combo speed up.
is going 7 miles, 70. Yeah, so the policeman is going to have to go faster to catch him, right?
Yeah, but he's trying to slow down to make that 90-degree turn. He's gonna
Not if
hold
he's-
us.
Not if he's, like one in some TV show.
Oh, good call.
Yes, sir.
Why do you have to take the derivative of everything before you?
It's a volume of a cone, and I got to tell you that I have seen many a problem very similar to this, almost like the exact same problem on pre-response AP questions. Okay, and so they love to do this because it's there's a couple of tricks that you got to know. Yes, sir.
What is a conical tank? What is that?
Who has a conical tank? The water cooler. Water cooler is when you fill up your phone.
Never seen that in a cone.
Like the office.
The cups.
Oh, like at the golf course.
At the golf course. Well, they're starting with a simple problem, but there's cylindrical tanks, a lot of cylindrical tanks, right?
Yeah.
But there are some conical tanks. Okay. Ice cream cone, yeah. Ice cream cone. Rocket ship. Rocket ship would have a conical front to it, right? Or something. You want to figure out how fast the bomb. Okay, anyway. Yeah, I showed you. Oh, I shouldn't say bad things on that. Okay. Water runs into a conical tank. The tank stands up, point down.
27,
It-
25, everyone remember that number.
It has a height of 10 feet and a base radius of 5. How fast is the water level rising when the water is 6 feet deep? So what do you know? What do you know?
The
What's this called?
water is coming in at 9 feet.
So that's called dV dt. You want, what do you want? Want?
DHDT.
Very good. Youngin, you want dH dt, right? You want dH dt? Okay, so I'm not going to worry about the numbers for right now. And so the first thing that, is the radius changing? Is the radius changing as the water level rises?
Yes.
Yes. Is the height changing as the water level rises? Yes. So you have two things going on, okay? So let's just write the formula for the volume of a cone. What's the formula for volume of a cone?
1/3 pi r.
1/3 pi r squared h, right? So unfortunately, I need to find dH dt, and they give me dV dt, but they don't give me dr dt, right? Okay? And so either I have to know dr dt, or I have to figure out a way to get rid of that r in my equation, okay? Which is not too bad, because look, they draw this little triangle here, and do you understand that this filled in part of this cone is similar to the cone itself? Remember this from geometry? Right? So now you could write a proportion. What's a proportion I could write based on this? 5 is to 10. Okay, keep going, Logan. 5 is to 10 as r is to h, right? So now what I could do, my little trick here, okay, is to solve for R or H. Probably I want to solve for R. Wait, what are they asking? You want dH dt, right? So I want to solve for H. Yes? So I'm going
You
to
say you want to find the R?
You want to solve for
Wait, why
R?
is-
I want to solve for R and plug in something in terms of H for R. All right? Okay, so I'm going to solve this for R, which is pretty easy. So R equals 5/10. Is that right? Wait.
1/2
RH is, 5/10 times H. So R equals H over 2. Who has me a question? Yes, here.
Why isn't the height 6? Because it says like the water is 6 feet deep.
You have to, because
Yeah, that's what I was curious. Why can't you use that 6?
if I just plugged in 6 in here right now,
What's the point
Okay.
of them giving you that 60?
and because those rates are constantly changing, right? So first you have to take the derivative and then you plug in that 6. Yeah, because that's going to change depending on what that height is at a specific point.
So you
all
find
right?
the DHDT, you plug in 6.
From DHD, yeah. Then you would plug in your the base in it. So
Great
anyway,
question, Carol.
so then you get 1/3 pi times h over 2 squared, right? Because that's what r is. H over 2 squared times h, right? Which gives you the volume is, okay, pi over 12 h cubed. Did some quick simplification, pi over 12 h cubed. Right? 2 squared is 4 times 3 on the bottom, gives you 12 on the bottom. And you have a pi on the top, and h squared times h gives you h cubed. Yeah?
Yeah.
Gotta be good at algebra. Okay? So now I could write my dv dt is equal to pi over 12 times 3h squared times dh dt. Okay? And I don't even need to know the radius, right? I can know the height. I could plug in 5 in there, right? 5? 6. Oh, sorry, 6. Sorry. 6 in there. I can plug in 9 in there. And then I could solve that for dH dt. So I get 9 equals, this comes out nice and neat, pi over 12 times 3 times 36 times dH dt. And this goes away and turns into a 3. And 3 times 3 is 9. So that goes away as well. This 3 times 3 goes away with that, which turns into a 1, right? No? Yeah, I did some algebra. You can take lots of steps to do it. But you get that dH dt is equal to 1 divided by pi. And that's how fast the water level is rising, so whatever that is, which is approximately equal to, can someone take their calculator and divide 1 by pi? So it's changing by 0.32, go 3 decimal places. 318 feet per minute. Okay, so make sure you look at the units. This is in units, cubic feet per minute. So your answer is going to be in. So the water level is rising at a rate of 0.318 feet per minute.
Why is it not?
Why is pi on the bottom?